All right, my name is Roy Simpson, a professor of mathematics at Columbus River College, and in this video we're going to talk about why it makes sense to, when working with a second order linear differential equation of the form y double prime plus 2y prime plus 4y is equal to 5 sine of t, or any number times sine of t actually, why does it make sense to presume that the solution is of the form a cosine of t plus b sine of t? In other words, why can we assume that our solutions are trigonometric in form? And we're going to start by mentioning a few things here. I'm presuming that we don't know how to solve an ordinary differential equation yet. And we're also going to presume that we know some language in the background. This is a second order ordinary differential equation right here. Is because the derivative is the highest order derivative is second, or the second derivative. And then it's linear because all of the dependent variables, which are y, and their derivatives are to the single power, a unit power, and their coefficients do not involve y or functions of y. So that makes it linear. So now let's think about why in the world would it be true that our solutions, that we can just by inspection tell that the solution to this, or a particular solution to this ordinary differential equation, is of the form a linear combination of cosine and sine here, where a and b are constants. Then once we're done with that, we'll find a particular solution. But so let's go ahead and think about this. I'm going to see if you can just conjecture it. This is not anything against you. It's just to see if you can conjecture a reason why this must be true. Okay, so the real reason is that if you were to assume, for example, that the solutions are of the form, and let me get a good pen going on here. Let's suppose that the solutions, SPS to me always means suppose the solutions are the form y is equal to a polynomial, for example. So I'm just going to write as a sub n x to the n, oops, that's supposed to be an n, but I wrote a 4, x to the n plus a sub n minus 1, x to the n minus 1, and so on and so forth, all the way down the line. So we think that our solutions are polynomials. Let's suppose that's true. Well, then when you take the first and the second derivative, you're going to end up with more polynomials, right? And so if that's the case, that would imply that y double prime plus 2y prime, which is equal plus 4y, would equal some type of polynomial, actually. So right now we can easily say this cannot be the case, that y could not involve polynomials because, well, actually, I should say y could possibly involve polynomials, but they'd have to be low-order polynomials, and that's likely not going to happen. In fact, now that I'm thinking about it, y could not involve a polynomial, because if you think about it, even if y was equal to x, you would have a 4x there, you'd have a 2 here, and then you'd have a 0 there because of first degree polynomial. And then that means the right-hand side would be have to be 2 plus 4x. So that doesn't make sense. So let's go ahead. Now I'm going to go ahead and cross this out because this can't be the case. Let's make another supposition. What other kind of functions do we know that it could that are possibilities? And by the way, this is important for us to make the investigation like this. So another possibility for functions. Let's see, when we went through algebra, we learned about polynomials. We learned about radical functions. I'm going to stay away from radical functions, mainly because if you take derivatives of radical functions, let's say y is equal to x to the 1/2 or something like that, when you take their derivatives, then y prime is going to be another radical function with a negative exponent, and y double prime is even worse, right? So negative 1/4 and x to the, I'm sorry, I'm writing x's when they should be t's, but that's not that big of a deal. Negative 3/2. I'll remedy that in my future examples. But in this case, if we're to try radical functions, that also would not work out because the right-hand side, when you add up these combinations of y double prime and y prime and y, it would not be sines. So you can kind of see immediately what's going to happen. The only way that we can get a right-hand side to involve a sine is if our function initially had a sine or a cosine. So if it was the case, going back to using my blue pen here, if it were the case that y was equal to some constant, and we write a parameter like a constant, like a, because we just don't know what the coefficients are. They could be really anything. There I go. I'm writing the t now, plus b sine of t. If that's what y is, then that would imply that y prime is equal to a negative a sine of t plus b cosine of t, and then finally y double prime would be a negative a cosine of t and a negative b sine of t. Now, I'd like to see if you can figure this out. If this is the case, if our solution is of the form a cosine of t, b sine of t, or plus b sine of t, I wonder if you can, going back to the original differential equation and plugging in those values for y double prime, y prime, and y, and setting it equal to 5 sine of t, I wonder if you can figure out what the values of a and b are going to become. So why don't you go ahead and try that on your own? Take a few minutes, just practice this, and then when you come back, we'll see how, if you get it wrong, you can see how it works out. If you get it right, well, you just see how it works out anyway. Okay, so go ahead and try that on your own. All right, so here's how it's done, and I don't know if you got it right or wrong, but we know that's the differential equation is y double prime plus, was it 2 or 4? 2. Plus 2y prime plus 4y, and it's supposed to equal 5 sine of t. So I'm going to insert y double prime, negative a, actually, I'm going to do it by the magic of this guy. So I'm going to insert y double prime, this guy right here, plus 2 times y prime, this guy right here. Don't you wish you can do this on a piece of paper, right? Plus 4y. This might go off the page. I'm not 100% sure. It's very close, right? And now we're just going to simplify this. This is equal to, well, let's count up all the cosines. Everything with cosines in it, I'm going to collect. So if I collect everything with cosines, I have a negative a of them from this guy. Okay. I have a positive 2b of them from this guy. And I have a positive 4a of them from that guy. So let's go ahead and finish writing that out. A positive 2b and a positive 4a of them. And those are the cosine of t's. And then as far as sines of t, using a different highlighter here, I have a negative b of them, I have a positive 2 negative a of them, and I have a positive 4b of them. Okay, so let me go ahead and write that down. I have a negative b plus, minus 2a. And then let's see, the sign is plus 4b. And those are all the signs. And in the end, I want that to be 5 sine of t. Remember, that's where we want to go. This creates a system of equations. This is called comparison of coefficients. So let me go ahead and write that down. Comparison of coefficients. This is a method that we're going to use later on in our differential equations course. But for now, just know that what you're doing with comparison of coefficients is you're comparing the coefficients of like terms on either side of your equation. So, for example, the coefficients of the cosine of t. Well, for the cosine of t, and I usually, when I do this in class, I build a grid like this, and I have the left-hand side, and I'll compare it to the coefficients of cosine of t on the right-hand side. So on the left-hand side, the coefficients of cosine are going to be, let's see, negative a plus 4a is 3a plus 2b. And on the right-hand side, the coefficients of cosine of t, well, there is no cosine of t, so it's just 0. And compare the coefficients of sine of t. On the left-hand side, we have a negative 2a, and we have a positive 3b. And on the right-hand side, the coefficients of sine, 5. All right, that's a system of equations. We can actually find out what a and b are based upon the system of equations, and which is all the way back to our algebra days, right? So we have 3a plus 2b is equal to 0, and we have negative 2a plus 3b is equal to 5. And now we go ahead and get, you can either use substitution or elimination. I have a habit of using elimination, so I'm going to multiply both sides of that top equation by 2 and both sides of the bottom equation by 3 to get, and you guys know how to do this, so I'm not going to really belabor the issue. It gets me 6a and a negative 6a. Those will cancel. I get 4b and a 9b, which will imply that I have 4 and 9, 13b is equal to 0, 15. Well, that's kind of ugly, isn't it? 6 and negative 6, 4 and 9. Yeah, well, that's exactly what it is. So that implies that b is equal to 15/13. And now I can substitute that into either equation, and I think I'm going to substitute that in the top equation here to find out what a is. So if I do that, that will imply that a is equal to, let's see, 15/13, so that'll be 30/13. Subtract it and divide by 3, that's negative 10/13. Let me just double check my mathematics. 15 times 2 is 30. Subtract is negative 30/13. Divide by 3 is a negative 10/13. That's actually true. So, what does this mean in the long run? That's kind of a tough question for me just to kind of throw out and say, what do you think the A and B are, right? That's a lot of work. You may have spent quite some time doing that. But what that basically means is that our solution, which was supposed to be y equals a cosine plus b sine, our particular solution for this ordinary differential equation is y equals negative 10/13 cosine of t plus 15/13 sine of t. And that's it to this problem. Notice that I should kind of give you a fair warning for the future, is that for this differential equation, there's actually more to the solution than this. We call this a particular solution because this is parameterless. In other words, there's no constants in the solution. So let me scroll down. Notice there's no parameters. There's no C1 and C2 in the solution. But it turns out that this is not the full solution. This is not the general solution, is what we would say. The general solution to this actually is much bigger. It involves parameters, but this is one of the infinitely many solutions to this differential equation. And so as you move forward in your course, you'll be able to find the most general solution, but finding a particular solution ends up being the hardest part. Finding the general solution, or at least the non-particular part of the solution, is not actually terribly bad in the long run.